So a few of you asked for this, so I'm going to very quickly finish answering a few of the questions on the the final exam from winter 2019. So in the last video in class, we ran out of time just before question number 19. So I'll start with question 19. So in question 19, it says that you have a red box that contains three numbers, 0, 1, and 2. You have a blue box which contains two numbers, 0 and 1, and you have a green box which contains two numbers, 1 and 2. All right. So there's a procedure that executes in two steps that's described here. So in step 1, you're going to choose a number that you're going to call x uniformly at random from the red box. So x could be 0, x could be 1, or x could be 2. If x is 0, then you're going to choose a number that you call y uniformly at random from the green box. This green box. So since y is coming from the green box, that means it could be 1 or it could be 2. If x is 2, you're going to do the same thing. Choose something from the green box, which could be 1 or it could be 2. And if x is 1, then you're going to choose from the blue box a number that you'll call y, and that thing could be 0 or it could be 1. All right? And finally, z at the end of this is defined as the max of x and y. So the maximum of those two values. So for example, if we choose x equals 0 and then y equals 1, then the maximum of those two values is 1. If we choose x equals 0 and y equals 2, the maximum of those two values is 2. X equals 1, y equals 0, the maximum is 1. X equals 1, y equals 1, the maximum is 1. X equals 2, y equals 1, the max is 2. X equals 2, y equals 2, the max is 2. So these are all the possible outcomes, and down here at the leaves of this tree are the values of z for each of the possible executions of this thing. And the question asks, what's the expected value of z? Well, for that, we need to know what the probabilities are of each of these outcomes, these values for z, because of course the expected value of z is just the sum over, let's call it k, not to confuse things, of k times the probability that z is equal to k. So all of these outcomes here. All right, so each of these three choices for x occurs with equal probability. So x is chosen uniformly at random from the red box. So each of these three branches occurs with probability 1/3. And then no matter what happens after that, we're choosing from a box. It's either the blue one or the green one, but that box contains two values. So each of these happens with probability 1/2. And the choice that we make for x in the first step is independent of the choice that we make for y in the second step. So each of these occurs with probability 1/6. Okay. And so now we just have to sum this up. The expected value of z will be 1/6 plus 2 times 1/6 plus 1 times 1/6 plus 1 times 1/6 plus 2 times 1/6 plus 2 times 1/6. Let's write that out carefully. So this is 1/6 plus 2/6 plus 1/6 plus 1/6 plus 2/6 plus 2/6, which is, let's see, 1, 2, 3, and plus 6 is 9/6, which is 3/2. So we'll check the answers. Is there an option that's 3/2? Yes, that's answer B. And that's for question 19 on the exam. Okay. Next, question 20. For question 20, n is bigger than or equal to 2, and we have a string C1 to Cn of length n, where the values in that string, so we have C1, C2, C3 up to Cn. Each value of Ci comes from the set 1, 2, or 3. And each of those is equally likely. And the question asks about this random variable x, which is equal to the number of values I, where I can be 1 all the way up to n minus 1, such that Ci times Ci plus 1 is odd. Okay. So x is the size of that set, the number of these indices I, where I take I, Ci plus 1, I multiply them together, and if the result is odd, then I include that thing in the set. So I count that value of I. All right. So then this is, x is counting the size of a set, and even the question suggests that you should use indicator random variables. And I think the choice is fairly obvious here. You'll just say that xi is equal to 1 or 0, and it's equal to 1 if Ci times Ci plus 1 is odd, and it's 0 otherwise. Okay. Then, of course, x is just the sum I equals 1 up to n minus 1 of xi. And as usual, now that means the expected value of x is equal to the expected value of that sum. And all of you remember now that what we always do as the next step here in this recipe is to say that the expected value of the sum is equal to the sum of the expected values. And so all we need to figure out now is what's the expected value of xi. And remember that the expected value of an indicator random variable is just the probability that xi equals 1. In this case, that's just the probability that Ci times Ci plus 1 is odd. That probability isn't hard to figure out. So if we take an odd number and we multiply it by an odd number, we get an odd number. But if we take two even numbers or an even number and an odd number, we get an even number. And so the only way CI times CI plus 1 is odd is if both of these things are odd. So this is the probability that CI and CI plus 1 are odd. CI and CI plus 1, these are independent. That was given in the question. So that's the probability that CI is odd times the probability that CI plus 1 is odd. What is the probability that CI is odd? Well, there are 3 choices for CI. Each one is equally likely, and 2 of those choices, 1 and 3, are odd. The other one is even. So this is 2/3 times 2/3, or 4/9. So now we know the expected value of xi for every xi. So this is the sum I equals 1 to n minus 1 of 4/9. So that will be 4/9 n minus 1. Now we have to look at the answers and see if there's any that match. And indeed, answer D has exactly this form, 4/9 n minus 1. Okay. So for question 20, the answer is D. Now, you would probably like me to do question 21, but I won't, because question 21 is actually a question that's on your 4th assignment. So do the 4th assignment and you would certainly be able to answer that question, or don't do the 4th assignment and have a look at the sample solutions that will be posted as soon as the assignment is due, and you can find the answer there. So that leaves question 22. Question 22 says, this is about a couple who's having children. Each child is a boy with probability 1/2, and it's a girl with probability 1/2, and all of those things are independent. So the sequence of boys and girls that appear is a sequence of independent choices. And the couple stops having children as soon as they have 2 boys or 2 girls. So G, so as soon as they have 2 of one gender. Okay, so G is the number of girls. B is the number of boys. And the question asks about B and G, and this is one of those independence questions. So option A is the random variables G and B are independent. Option B is the random variables G and B are not independent. And at this point you can stop reading the other options because one of the first 2 things has to be true. Those are complementary propositions. One of them is false and one of them is true. So one of A and B is the correct answer. Now we just need to figure out if these 2 random variables are independent or not. And for that we need to remember what it means for random variables to be independent. For events, there was a very simple definition that applied to 2 events. It just says that the probability of both of those events happening is equal to the product of their individual probabilities. For random variables, there's an extra layer required there, equal to one value, and G is equal to, B is equal to another value. That should be the product of the 2 probabilities, that G is equal to the first one and B is equal to the second one. So here, we can use our intuition a little bit and say, look back at the problem statement, and it says the couple stops having children as soon as they have 2 girls or 2 boys. All right. So that means that they will never have 2 girls and 2 boys, right? Because if they stop the first time they have their second boy, or the first time they have their second girl, then that means that there's only 1 child of the other gender. Otherwise, they would have stopped sooner when they had 2 child of the same sex. All right, so that suggests that maybe these things are not independent, and you would look for the violation of the definition of independence by looking at what's the probability that G is equal to 2, what's the probability that B is equal to 2, and what's the probability that B is equal to 2 and G is equal to 2. And if you're not careful, you may do a lot of work to figure all of these things out exactly, but what we've just said is that this probability here is equal to 0. Okay? So this probability is 0 because this never happens. The couple stops as soon as they have 2 children of the same sex, which means the other sex, there's only 1 child. Okay? So you never have 2 boys and 2 girls. On the other hand, by the end of this process, the couple either has 2 girls and 1 boy, or 2 boys and 1 girl, and there's nothing different about these 2 things. So either G equals 2 or B equals 2, both of them never happen. That's what we decided here. These things, so these are really complementary events, and there's complete symmetry. There's no difference between boys and girls. Each one happens with the same probability, and the rules are symmetric. You stop as soon as you have one of the same sex. So each of these must be equal to a half, and therefore the probability that the number of boys is equal to 2 times the probability that the number of girls is equal to 2 is 1/2 times 1/2 is a quarter, and in particular, that is not equal to 0. So it's not equal to the probability that the number of boys equals 2 and the number of girls equals 2. Therefore, these 2 random variables, B and G, are not independent. Okay. So that was question 22. The answer is B, the random variables G and B are not independent. Question 23 asks, you have a fair red die, so that's the cube with 6 sides on it with the numbers 1 through 6 on it, and a fair blue die, and you do the following experiment. You roll the red one, you roll the blue one, and you take the sum of the 2 numbers. Okay? And you do this until the sum of the 2 numbers is equal to 7. Okay? All right. And now you say, well, x is equal to the number of times you do the experiment. And the experiment is roll 2 dice and declare success if their sum is 7. Now, we saw in class, and more than once, or you can do it again yourself, when you roll 2 dice, there are 36 outcomes, and the number of each of them is equally likely, and the number of those outcomes where the sum is equal to 7 is 6. So this probability of success when we roll these two dice is 6 over 36, or 1 out of 6. And x is the number of times you do this experiment until you have a success. Now, if you followed my directions and carefully read the first page of the exam, or rather the first real page, not the cover page, there's a bunch of facts to remember there. And one of them reminds you what a geometric random variable is. And a geometric random variable is obtained the following way. It counts the number of times you need to run an experiment until you get a successful outcome. And the expected value of a geometric random variable is just 1 over that probability of a successful outcome. So on the front page, that's referred to as P. So P is the probability of success, is 1 out of 6, and therefore X is a geometric 1 over 6 random variable. So the expected value of X is 1 over P, which is 1 over 6, which is 6. And that's option A for question 23. Question 24 says, let n be an integer bigger than 2, and p and q are two real numbers between 0 and 1. So it sounds like p and q are two probabilities. So n bigger than or equal to 2 is integer. P is between 0 and 1, and so is Q. And the setup, if you read through it, it says, okay, there are two TAs called Alexa and Zoltan. And students are doing assignments. They're doing, n students each do an assignment. The assignment has 2 questions. It is Alexa's job to mark the first question of the assignment, and it's Zoltan's job to mark the second question of the assignment. But according to this question, which of course is not at all true, Alexa and Zoltan are a bit lazy, and Alexa only marks an assignment with probability P, and Zoltan only marks an assignment with probability Q. So for each assignment, assignment 1, assignment 2, assignment 3, and so on, Alexa decides, makes a choice. With probability P, she marks it. With probability 1 minus P, she doesn't mark it. And Zoltan, who has the same pile of assignments, assignment 1, assignment 2, assignment 3, he makes for each assignment, he makes a random choice. With probability Q, he will mark question 2 on that assignment, and with probability 1 minus Q, he won't mark question 2 on that assignment. And it asks about this value x, which is equal to the number of assignments that are marked by both Alexa and Zoltan. Okay, so x is a random variable, and it's one of these ones that has the form that we sometimes recognize as being amenable to using indicator random variables. The definition of x starts with the number of things that satisfy some condition. Okay. So the number of assignments that are marked by both Alexa and Zoltan. So then it makes sense to define this random variable xi which is 1 or 0, and it's 1 if assignment I is marked by Alexa and Zoltan, and it's 0 otherwise. Then, of course, x is just the sum I equals 1 to n of xi, and therefore the expected value of x is the expected value of that sum. As always, we take the sum of the expected values. And so now all we need to do is figure out what's the expected value of xi. Well, xi is an indicator random variable. The expected value of an indicator random variable is just the probability that it's equal to 1. In this case, it's equal to 1 if the assignment is marked by Alexa and it's marked by Zoltan. The probability that Alexa marks it is p. The probability that Zoltan marks it is q. And those two things are independent. So that means that the expected value of xi, which is equal to the probability xi equals 1, is just p times q. And now we finish up with this is the sum I equals 1 to n of p times q, which is just n times p times q. And that is option C on the assignment, or option C is p times q times n, but that's the same thing. All right. And then finally, there's question 25, but that's kind of a joke question. It asks you, who discovered the Fibonacci numbers? Was it Donald Trump? Was it the Italian mathematician Fibonacci, also known as Leonardo Bonacci, Leonardo of Pisa, or Leonardo Bigelow Pisano? Was it Alexandre Théophile Vandermonde? Or was it Keith Richards, the guitarist of the greatest rock band in the universe? You may guess that the answer is Fibonacci, and indeed that's the correct answer in this case, although, or at least that's the most correct answer offered here, although there is a rule about these things that things are almost never named after the first person who invented them. But in this case, at least Fibonacci invented them before Donald Trump, before Keith Richards. I can't tell you for sure about Vandermonde, but Vandermonde is known in this this course for a different thing, so that's probably not the answer. All right, so that's the end of the review, and good luck studying. Again, the advice that I have for you is just to do as many of those sample exam questions as possible.